dear friends, my dear friends, I have the pleasure of introducing Ivan from Australia. He's a senior software engineer whose passion lie in improving the developer experiencing by enhancing code health, optimizing workflows, and work towards nohumanerrors.com. When he's not thinking about security, informatics, or giving talks about his many projects, you'll find him nomming on Subway cookies or chasing bunny rabbits. Please I have the pleasure of introducing Mr. Ivan.
Thank you. Oh my God, it is great to be here. Thank you all for coming here. I did come here from Australia, so it means a lot to me as well. Awesome. So, while I am on a mission to mitigate human errors in programming, today what I thought I would do is show how you can do that by having Python eat your homework. What do I mean by that? Well, any student of maths would have probably had to do some kind of maths assignment or maybe some homework. And traditionally, you would have probably done this by hand, writing it out. Or in today's world of technology, you have styluses and tablets that you can do this on. Or you could have also done this with LaTeX. A lot of maths professors and teachers ask you to do this just so it's more readable and so forth. But I have problems with all of these methods, and that is that, well, to begin with, if you're writing it out by hand, it's quite easy to make handwriting mistakes, right? Like this symbol over here, is it an N, is it a 3? Who knows? And maybe your teacher might lose you some marks on that. But even if you do go through the effort of writing it up all in LaTeX, then I think there's still issues in that, okay, firstly, you have to essentially learn hieroglyphics to get LaTeX to display nicely. And even if you do go through that tedious step, then you're also left with the issue of, okay, is your work actually correct? You don't know. You'd have to go through by hand and double check it. And there's still possibilities of making typos, especially if you're converting it from being handwritten. And lastly, even if you do go ahead and check it all and so forth, there's still one more issue, which is there's nothing stopping your teacher from coming back to you and saying, that was great, here's another assignment, it's going to look exactly the same, but all the numbers are going to be different. And now you're stuck and you have to essentially do the whole process again. So I think that we can do better, and the way that I'm going to show you how is through using Python and SymPy and Jupyter to do so. So to do that, I've made like a sample assignment. Some of these questions did come from real work, and we're going to aim to try and submit this within the next 20 minutes. With that in mind, I understand this is not a maths conference, this is a Python conference, so some of the maths may go over your head. I'll try my best to make that not the case. But even if that is the case, the main thing I want us to focus on is not the maths, but kind of the principles that we're trying to apply. All right, so let's get started. The first question we have is this discrete maths question. And we want to show whether the following numbers can be represented as a sum of two squares. So we've got n equals a squared plus b squared. So here's an example number, 85, or for example, 250. That's equal to 81 plus 169, which is 9 squared plus 13 squared. So 250 is a sum of two squares. So as a reminder, because I'm nice, I will put some reminders of theories in my assignments. And to solve this problem, we can use this theory that says that a positive integer n can be written as a sum of two squares if and only if there is no prime p that divides n an odd number of times and for which p modulo 4 is 3. That's a bunch of maths. But the main thing that we want to start off with is we want to understand that all primes that divide n are also known as the factors of n. So for example, 250, the factors of 250 are 2 and 125, because you can divide 250 by 2 and get 125. And you want to keep doing this until you get to as many primes as you can. For example, 2, 5, 5, and 5. If you multiply them all together, another way of showing that is 2 to the power of 1 times 5 to the power of 3. And now we have it in this form that makes this formula a bit easier to apply, because we want to check if there is any p to the k such that these conditions hold. And for example, 2 here is the p, and 1 here is the k, and so forth. And what this looks like is, let me do one more thing. Cool, spoilers. What this looks like is like an algorithm, right? We go through the factors of a number, and we check when the conditions hold, and if they hold in the right way, then we return true or false. But this is great as pseudocode, but how do we actually calculate the factors? What we can do is we can import a method from SymPy, which is a Python for symbolic mathematics. And you'll see we import factor int, and if we run factor int, it will return to us those prime factors from here before, and it gives them to us as a dictionary of keys and values, which is great because now we can rewrite our code from before to take those factors, return them as items, sort them for good measure, and then we'll go through and apply the same process. So now if I run this code, you'll see that for the first part of the question, it says that 85 is a sum of two squares because it returns true. I reckon this is pretty good because I've shown my working out through writing a program essentially. But what do we think? Would my teacher accept this? No? Yeah, I reckon they would come back and say, you haven't actually written any maths. You haven't shown any working out. And I think I have, but we'll give them benefit of the doubt. And to do that, how about we just add some print statements? I've got a print statement here that tells you the factors of n. Then I've got some print statements in the for loop that just tells you what's happening in each step. And then some final print statements for if, whether it's true or not. And so now that I've run this, you can see, okay, for 85, the factors are 5 and 17. And then we check 5, and that doesn't hold. And then we check 17, and that doesn't hold. So 85 can be written as a sum of two squares, and then we say it's true. And I think also that's pretty good, but again, my teacher will probably come back to me and say, all you've done is output text. You haven't actually written any maths, and we'll give them the benefit of the doubt. And to do that, we can actually use SymPy's feature where it lets you visualize a lot of the maths. And the way we can do that is using visual equals true. And so if we run this, instead of before where it prints this dictionary, which is helpful if you're doing programming, you can get it to print out some pretty looking LaTeX. And this is really nice because now we can actually start to show working out in our notebook. There is one more thing though, and that's that we want to actually write some equations. And to do that, we can import the EQ method from SymPy. And then we can use it to say, okay, 250 is equal to the factors of 250. And if we run this, okay. So SymPy has a couple of gotchas, and this is one of them, in that it will do a lot of things for you to the point of actually evaluating what this would be. And that's nice. But it's not really nice if you want to show some working out. So what we can do is we can use the evaluate equals false argument. And that essentially tells SymPy, hey, for this operation, don't actually do any evaluation. Just print out what you want to visualize. All right. So now that we have that, we can extend our our solution a bit further, we've got this display from before, which essentially just displays this part here. And then we've also added some displaying of Markdown, so we can add a tiny bit of LaTeX just to make it a bit more legible. And if we run this now, you'll see that it looks a lot more like an assignment written in LaTeX. You've got the nice equals, you've got all the checking, the numbers stand out, all the operations stand out. So it's really nice. And I reckon by this point, it's actually quite good to go ahead and submit it, because we've shown our working out through our code. We've shown our working out through essentially displaying the steps one by one. And then we've got the answer for each of the questions. That being said, there's also one more thing that SymPy is really good for, and that is that it actually has a lot of these things for you. So for example, we don't have to go through and calculate the sum of squares manually. If you just want to get the answer, you can do that using the sum of squares method. And what we've done is we've used this down here, where after we calculate the answer, we can then use the sum of squares that's built in to give us essentially like a double checking method. And if I run that, you'll see that right at the end, we give an example, which is, okay, 85 is equal to 6 squared plus 7 squared. And that's really nice, because now we've done the entire life cycle of a maths assignment. All right. Are there any questions? Awesome. Well, I'll also take questions at the end. Let's move on to the second question, which is a calculus question. And you may remember this from university or high school or etc. We have a curve, and we want to calculate the x and y intersection points. We also want to calculate the curve's vertex, and we want to plot the curve. What can Wolfram Alpha do? Well, if we put it in, we'll see that it actually plots the curve for us. It tells us what the roots are, the x intersection points. And then it also tells us, it plots it out. It tells us where the maximum value is, and that's where y is equal to 4. And finally, I think that's everything. But it does suffer a little bit in that I can't take this and screenshot it and send it to my teacher. They're just not going to accept it. Maybe if I paid for the step-by-step solution, they will, but I don't really want to pay for it, and it's probably not going to be as nice. So how about we go through and try and implement this ourselves? Oh, it also calculates the derivatives. That's what I missed. Cool. Okay. So to do that, we can first import the x symbol from SymPy. And what that lets us do is it lets us rewrite our equation in terms of basic Python maths. So we use x here to write our equation, and if we run this, you'll see that it easily and nicely prints it for us. Once we've done that, we can also import a function. And what the function lets us do is it just lets us nicely display it. So if we run this, you'll see, okay, we've got y of x is equal to this equation, which is really handy. All right, so now that we have it all down, let's calculate the first question, which is we want to get the y intersection point. So as a reminder, the intersection point is where x is equal to 0, and so what we need to do is substitute x to be equal to 0. SymPy has a method for that called subs. You give it the equation, and then you substitute x with a value of 0. And if we run this, you'll see that we get the value of 3, which is what we had before. But again, I think my teacher would probably not be happy about that because I haven't shown any working out. And I do still have a solution for that, which is, let's just display what the equation was and what we're doing, and we'll put 0 in the function here. But again, the teacher might say, no, not good enough. And so what you can use instead is this unevaluated expression object. And what this does is it lets us take a value that we don't want it to be evaluated and pass it into our equation. So to do that, I've done that here. this is basically the same code as before, except I've added this new equation here that has the unevaluated value of 0. And what that looks like is essentially what your maths handwritten would look like. You replace the x with the zeros, and now you can look at this and say, oh, it's equal to 3, and now you've shown you're working out. For the x intersection points, we essentially want to do the same thing, but we want to turn this equation to be with respect to x, or y, sorry, because we want to substitute y to equal to 0. And we can do this with the quadratic formula. For this case, we'll use the SymPy method. And what that lets us do is it lets us take any string that looks like maths, and it'll convert it into a SymPy object for you. So you see we take the quadratic method that we've written out, and then it will output it very nicely. And then what we want to do is we want to solve this with respect to x. So we import the solve method, and then we solve the quadratic with respect to x, and then we can display the two different quadratic equations. Now we take these equations, and we want to substitute in the constants that we had from the previous equation. So those constants are -1 for A, 2 for B, and 3 for C. So now if I run this, what I've also done is I've gone through both of the quadratic solutions, and then I substitute in the different values from the constants. And the other special thing I do here is I use this do-it method. And I use it because I've told the constants that they shouldn't be evaluated, but when I really want them to be evaluated, I just tell the equation, hey, whatever you have that's unevaluated, actually do it. And then you'll see we're left with our two equations where we have the values substituted in, and we can see now that the x-intercepts are where x is equal to 3 and x is equal to -1. Of course, SymPy also has methods to fast forward this as well. You can just tell it, solve my y equation with respect to x, and you'll get the values -1 and 3. Which is really handy if you don't actually, maybe your work is a bit more complex and you don't want to go through and resolve the quadratic method. All right, for question 2.3, we want to calculate the vertex, and to do that, we want to find where the derivative is equal to 0. We can do that with the diff method, which differentiates it with respect to x, and you'll see on one side we've got our working out, and on the other side we've got our solution. Now we want to solve for y equal to 0, so we solve this equation here with respect to x, and then we substitute x is equal to 1, and now we see that the maximum point is at 1, 4. Lastly, we have the question to plot, and this is very simple. You import plot, and you plot the equation. And now you see we have what Wolfram had shown before. And the other thing to note is that you don't actually need these lim statements either. I just have it here so that it's a bit easier to read. Cool. Are there any questions on that? Awesome. All right. Let's go to question 3. And question 3 is the hardest question. But essentially what we're doing here is we're using the same question as before, but instead of it being in 2D, we do it in 3D. And what we want to do is we want to calculate where the maximum value is. And so before, where we had the equation in terms to x and y, here we have it in terms of u1, u2, and let's say z, for example. This is a bunch of text. You can read it later. But the main thing I want to get across here is that imagine that this is a curve where you have, let's say that you're Apple and you want to sell iPhone minis and iPhone Pro Maxes. They're both very similar, and selling one means someone else won't buy the other. They also have shared components. And that's essentially what all of these constants do. They represent what is the cost of producing this one as opposed to this, and how does that all factor in? Okay, so if we take that and we put it into Wolfram Alpha and we substitute all the equations as we want to, we will get a nice solution. It will give us where the value is at maximal and what that value is. Here it's got it as roughly 1 million. It doesn't tell you exactly, unfortunately, but more importantly, it doesn't give you any working out, even if you pay for it. But we can solve that. So to do that, we'll import some symbols, as we did before, but we'll make them a bit friendlier with LaTeX, and then we can rewrite our equation, we import our function, and then we can display it as we had before. Once we've done that, we can now supply all of the constants, and then what we want to do is we want to calculate where the derivative is 0, or the gradient is 0. And that's how we get the optimal profit. To do that, we need to calculate it with respect to x and y, essentially, or in this case, u1 and u2. And this is essentially what this block does. And you can see it's got, okay, here's the symbolic form on the left, and then also the expanded form on the right. And at the various stages, we expand it a bit more and more. Now what we want to do is we want to solve this with respect to u1. And again, we just use the solve method. And all this is doing is just substituting. It's doing really tedious work that we could do by hand, but we'll probably make some errors. Once we've done that, we can substitute u1 into the equation with respect to u2. And what that does is it lets us get rid of all of the variable constants of u1 and u2. And if we run this, you'll see that this is what we're substituting it into. And now we want to solve with respect to u2. And you'll see what I mentioned here. Now we can figure out what the value of u2 is just by substituting in all the constants. And so I can do that, and we get our first value of 7,000. Right, so this is handy. We've gotten to one step of the solution, but it's still a bit problematic. And that is that we now have to calculate the next part, and we could copy it, but then it will look messy, and what about for future things? So what we can do instead, now that we're in the world of Python, is create a function where we can substitute all those values in. So I've got the equation, the function, the parameters, what the output symbols should be, and the constants. And now all I've done in this function is basically duplicated all of this code above, but I've also put in a for loop to go through the different values. And once I run this, you'll see that we've gone through and calculated 7,000 again, but then we've also gone through and calculated the value for u1, which is 4,000, roughly. And now we have what where our optimal maximum point is. So then we can take all of those values and substitute it in, and we'll get our value of 10, is that a million? A million, yeah. Awesome. Okay, so let's go through the appendix, and then we'll jump back a bit. The main things that I want to cover here is that SymPy lets us do a lot of this work for us. And it wouldn't be possible without contributors like you. It's not every day that you have someone that is at the intersection of computer science and maths. Not everyone's going to look at a maths paper and be like, oh yeah, I understand that. I can write that up as an algorithm. And even if there are those people, there's just so many maths algorithms that need implementing. So if you're interested, please go and contribute to SymPy. Like, they have so much work that's needed. Last time I screenshot this, it's like 4,000 issues. They would really appreciate your help. It doesn't even have to be re-implementing algorithms or maths papers. It can be very simple things as well if you want to get started. The other thing is I've used Jupyter to display this whole notebook. And that's really powerful because now I can, save and export the notebook as HTML. And if I remember how to, cool, okay. And now we have the whole notebook printed as HTML. And this is great because now we can like command print, print it out in paper or print it as PDF and then send it to our teacher, and they can read it and see all the methods that we've applied. Awesome. If you want to check out this notebook and any of my other work, you can scan this QR code, or you can go to python-8-my-homework.nohumanerrors.com. Other than that, I would love your feedback. I'm always looking to improve. Please let me know how. But yes, thank you to you all, my partner and friends, for watching. And I have a bit of time for questions. Thank you. You want to send them to the mics for questions? Okay, great. Hello.
Testing, great. I just had a quick question about the unevaluated expressions are presumably exact, and then at the end, when you evaluate them, you end up with an approximation.
Yes.
What if you were asked for a simplified but exact solution? Can SymPy do that?
Like if you want to express an irrational digit as a fraction?
Sure, or keep some roots in there instead of
Yes.
evaluating it out as a decimal.
That's a good question. I'm not sure. I believe it's possible. I'm not super familiar with it. You would have to check the library, but I'm like 80% sure that it is a case where you can essentially choose what your unevaluatedness is.
Cool. I'll look it up. Thanks.
Awesome, thank you.
Hey there, can you hear me?
Yes.
That was a great talk, thank
Thank you.
you. I was a math major myself, and can you talk about like the specific use case? Who's your customer or person that would use something like this? Would they, especially given that they could also use AI tools, you know? Yeah.
Yeah, I think this came out of me realizing that like me going ahead and doing a lot of maths manually is really tedious, and I know Python, I can go and do it for myself. The nice thing about this is that it forces you to implement the solution in code, and it essentially makes you realize and think about what am I actually doing with the maths. And for me, it helped me a lot more to understand, oh, this is all that this theorem is doing, and I can write it out by hand. And I feel like if you use AI, you kind of miss out on a lot of that because it just gives you the answer, and it's also not exact. Does that answer your question?
Yeah, thank
Cool,
you.
thank you.
Hello, this has been a great talk.
Thank you.
Under the impression from this entire thing is that actually doing the assignment with this would be a little less practical and a little messier and, how to say it, rigid. And I'm under the impression it will be better for submissions rather than actual practice and exercise when writing on paper would be better. What's your thought on that?
Yeah, I use this method to submit, but also actually work through the solution. I think I get what you mean. There is like, in one hand, you don't want to go through all this programming just to get an understanding of how it all works. On the other hand, it's very useful because you can slowly iterate on it, and then once you have it all working, you can submit it. I mean, there's a balance, right?
Yeah.
If you end up using this to solve an exam or Like you might not have this in an exam, and if you use it too much, you don't use it correctly, then you will struggle there. Does that answer your question?
Yeah, I might just be a little old-fashioned, but like, yeah, I get it. It's a great implementation anyway.
Thank you.
Great
Thank
talk.
you. Thank you. Oh, hi. Sorry, I
Oh, no,
forgot.
no worries. The quadratic equation is fantastic for very well-behaved values of A, B, and C. Do you know if SymPy takes care of extreme values of B, where B is very large or very small? That's when the quadratic equation blows up completely. Now, this is part of
Yeah.
my numerical analysis. So.
I'm not sure, but we can just try it. Where were we? Okay, so we had our equation defined over here.
Yep,
Let's give it like 1,000,000,
that's our 10, yep.
big number.
Yeah.
Oh, that's for the A. Let's what was this before? Whatever. I'll make it 1. Oh, sorry. This is the quadratic. We actually want. This was 2. My bad. Where did we define? Oh, we defined it up here. Okay. And then let's go with this one. That's the quadratic.
Okay.
Let's just go straight to the y equation. It's got the square roots and all, so does that answer your question?
Oh, I cannot wait to play with this. Outstanding.
Wonderful, thank you. This is also like a nice thing about it, right? Like we can go through and update we can go through and update our numbers here and put in like 49 and 343, and we can rerun this and we'll, instantly works for us. Yes?
Hi, thanks for the talk. It was great. My background's in physics, and I remember an exam I had where I totally blew up some symbolic manipulations, and my logic was perfect, but I didn't get a perfect grade because of that. So I guess my question goes to like, what do you think is the future of symbolic math that we all used to do, at least people in my generation, by pen and paper, and now we have all these tools that can basically make no mistakes?
Yeah, it's a good question. Sorry? Okay. Okay, great. Okay, so sorry, yes, that was the last question. To keep it short, it's a hard line between like doing rote learning to kind of memorize the thing that you're trying to solve, but also at some point, like to gain an understanding of what maths is, that's important. But there's also this distinction of like, at some point you don't actually need to go through and do it by hand anymore. You can use something like this. And maybe to begin with, this is what people can use to do that more heavy work and play around with it. I would like to see it more on the other side as well, where when you are learning, you can use this as a tool for learning rather than just solutions. But we can talk more after. Awesome. Thank you so much, everyone.